Hopefully everybody can see that in presentation mode. Okay, great. I'm seeing a thumbs up. And I'm going to get the pointer up here too. Okay, so as been mentioned, I'm going to be presenting today on some modeling of new TB treatment regimens. Thanks everyone for coming. I'm planning to present for about 40 minutes, so hopefully we'll have lots of time for Q&A at the end. So I want to start just by providing a bit of context. I think probably most of you on this call already know that how someone's TB is treated in any given setting is really strongly determined by the rifampin susceptibility of that TB. And in many settings, treatment decisions should and sometimes are guided by susceptibility testing for other drugs too, but we have this sort of clear stratification of treatment strategy, guidelines, outcome reporting, et cetera, by rifampin-resistant status. In general, RIF-resistant TB regimens have been longer, less effective, and had worse side effect profiles than RIF-susceptible regimens, resulting in much higher treatment success for RIF-susceptible TB than RIF-resistant TB. And as Finn alluded to, there have been several advances in the past few years in the development and evaluation of new TB treatment regimens, both for RIF-susceptible and RIF-resistant TB. And I'm sure that most of you are aware of some of these. One that I want to highlight for RIF-susceptible TB is Study 31, which was published in 2021 and found that a 4-month regimen for RIF-susceptible TB was non-inferior to the 6-month standard of care. So a sort of example of a treatment shortening success there when a lot of shorter regimens had failed to demonstrate non-inferiority in previous trials. And then for RIF-resistant TB, there's been a ton of development. One that I just want to highlight quickly is the BPAL-BPAL-M regimen, which was found over a series of trials, I think published in 2020 to 2022 or 2023, to be much safer and more efficacious than previous RIF-resistant TB regimens, and also substantially shorter, so only 6 months versus 9 to 24 months of previous regimens. And since the BPAL-BPAL-M results have been published, there's been a lot of other development in the RIF-resistant TB space too, and other sort of somewhat shorter, although I don't think 6-month regimens shown to be pretty efficacious and safe. There's still, however, a lot of room for improvement here. So there are concerns about the safety profile still of some drugs in current regimens, including for BPAL, for example, linezolid. Still efforts to try to make these regimens easier for patients to take, and that could take the form of further duration shortening and or better side effect profiles. Some concerns about the evolution of drug resistance, particularly with bedaquiline and BPAL, and some sort of concerning numbers coming out of South Africa that make us a little worried about the longevity of this regimen. And then affordability also remains an important consideration, both in terms of the prices of drugs themselves, as well as other components of treatment that need to accompany those drugs. And there is now still a tremendous amount of development and innovation happening in the TB therapeutic space. So this slide just shows all of the clinical trials and preclinical studies that were being done for TB therapeutics as of October 2024. And I'm not going to talk about all of these in detail, but I just want to use this slide to illustrate that there are more TB treatment options becoming available and going to be available on the horizon. And with those options come important questions about which regimens and or broader treatment strategies are best. And mathematical modeling is really well placed to help us examine some of those questions. To help guide drug development efforts, also, the WHO published in 2023 revised target regimen profiles, or TRPs, for TB treatment. And in the sort of words of the WHO, these are profiles that seek to guide the development process toward important regimen characteristics corresponding to the needs of end users. So those would be patients, clinicians, health systems, et cetera. So what these TRPs look like is a set of characteristics characteristics and target values for those characteristics for RIF-susceptible TB regimens, RIF-resistant TB regimens, and pan-TB regimens. And I'll talk a little bit more about what we mean by pan-TB regimens a little later in this presentation. Characteristics would be things like efficacy, safety, duration, et cetera. And for each of these three types of regimens, we have minimal and optimal targets that were published. So in light of these recent and ongoing advances in drug development and to inform the TRPs, we conducted a couple of modeling analyses that I'm going to highlight today. Both of these analyses were aimed at answering broadly the question of what should priorities be for future TB regimens from the perspective of improving treatment and health outcomes and the perspective of reducing costs, or at least not increasing costs. The settings where we conducted both of these analyses were India, the Philippines, and South Africa. And the first one that I'm going to talk about was really focused on these regimen characteristics that were included in the TRPs, aimed at answering the question of, compared to current RIF susceptible and RIF-resistant standards of care, what characteristics are most important to improve upon? So would we rather have a future RIF-susceptible regimen that has better efficacy or shorter duration? Would we rather have a future RIF-resistant regimen that is easier to take in terms of improving adherence or shorter duration, et cetera? And then the second part of this presentation is focused on a bit of a broader question, which I've framed as which types of regimens should we be prioritizing? And here answering the question of whether it's more important to try to continue to improve upon existing RIF-susceptible and RIF-resistant regimens separately, or if we should be prioritizing regimens that can address some of the shortcomings of this RIF-resistant stratified approach that we have in TB treatment. And here again, we'll be talking about potential pan-TB regimens that could be used to treat both RIF-susceptible and RIF-resistant TB. So I'm going to move into describing the methods for part one. This is the analysis focused on regimen characteristics. And I'm going to talk first about how we modeled and estimated health outcomes, particularly patient cures, and then I'll discuss our costing approach. So again, the purpose of this part one analysis was to inform the TRPs. We constructed a quite simple patient cohort state transition model, and we used this model to evaluate a series of hypothetical novel regimens. These are regimens with improvements upon one or more of the characteristics included in the TRPs. So we looked specifically at efficacy, duration, ease of adherence, forgiveness, and safety. And I'll talk about what we mean by each of those in the coming slides. And then we compared those novel regimens against standards of care. For RIF-susceptible TB, we modeled the standard of care as being the 6-month HRZE regimen for most patients. And for RIF-resistant TB, we modeled the standard of care as being the 6-month BPAL-M regimen for most patients. So the model was sort of entirely stratified. Either we ran it for RIF-susceptible patients or RIF-resistant patients. We didn't consider, for example, RIF-resistant patients that might be assigned to a RIF-susceptible regimen because we did not think that improvements to those respective regimens would really affect that patient group. They're going to have poor outcomes regardless. And then the primary outcomes that we looked at here were the percentage of patients durably cured with each regimen and the prices at which these hypothetical improved regimens would be cost neutral compared to the standards of care. So our very simple model of patient cures consisted of three main components. For each regimen, we had an efficacy value, and that efficacy value would be consistent with how efficacy would be measured in, say, a clinical trial. And then the probability of cure was a function of that efficacy value modeled by regimen discontinuation over time and modeled by intermittent inadherence to the regimen while remaining on treatment. the kind of construction of our model is shown here. We modeled either a RIF-susceptible or RIF-resistant cohort as initiating a given regimen, and then those patients were assigned to one of 4 adherence categories, and then each week on treatment, they could either sort of remain in their adherence category and stay on treatment, or they could become lost to follow-up. And then the probability at the end of the model time horizon, which would be 6 months, for instance, for the current regimens, the probability of durable cure was based on their adherence category, the amount of time they spent on treatment before loss to follow-up, and the efficacy of that regimen. We also made some slight modifications to efficacy to account for isoniazid monoresistance among RIF-susceptible patients and fluoroquinolone resistance among RIF-resistant patients. And I'm happy to talk about that more during the Q&A if people have questions about that. So this slide describes how we adjusted for regimen discontinuation. So how we did this is we modeled a non-regimen varying weekly risk of discontinuation or loss to follow-up of 0.3%. And this translates into approximately a 1% probability of loss to follow-up per month, or for 6-month regimen, this would be around a 6% probability overall. This was based on evidence from both RIF-susceptible and RIF-resistant regimens, including a systematic review that's rather old now, and a more recent cohort study from South Africa. And this is broadly in line with global treatment outcomes in terms of proportion loss to follow-up. What this means, because this risk is non-regimen varying, is that we will have more cumulative discontinuation for regimens that are of longer duration. And then the second part of this was to estimate a relationship between the percentage of time completed of that regimen before discontinuation and the effect that that would have on probability of cure. And that relationship is shown in this figure here. So we estimated that patients who completed a third of regimen before discontinuation, so this would be like 2 months on a 6-month regimen, had about a 70% relative probability of cure, and those who would complete, say, 4 months of a 6-month regimen would have closer to an 80 to 85% probability of cure. These 2 points here are based on trials of 2 and 4 month HRZ regimens, kind of historical trials, and looking at relative efficacy of those. We extrapolated linearly for loss to follow-up at other time points. And then for lack of data for BPAL, BPAL-M, we assumed this same relationship held for that regimen and for other sort of hypothetical novel regimens. The other adjustment that we made to estimate probability of cure was based on regimen ease of adherence and forgiveness. So the discontinuation that I just talked about is linked to the duration characteristic, and this adherence relationship is related to the ease of adherence and forgiveness characteristics. A more forgiving drug is described as the literature as one that allows for robust therapeutic outcomes, even with common patterns of imperfect adherence. And in this analysis, we specifically defined forgiveness as the degree to which regimen efficacy or probability of cure is unaffected by suboptimal adherence. So this is a characteristic that would be determined typically by the pharmacokinetic properties of drugs in a given regimen. For HRZE, our forgiveness parameters in the model drew upon data from a TB Reflect study, which included analyses of the control groups of 3 trials that were evaluating 4-month quinolone-containing regimens and looked at the relationship between adherence in terms of percentage of total doses taken and relative probability of cure. And in particular, we compared the probability of cure, here this is unfavorable outcome, between those who were less than 90% adherence. This would be on average taking less, missing at least 1 dose a week, between those who were 90% or more adherent. And from these results, we estimated that that relative efficacy was 77%. So those who took less than 90% of doses had a 33% lower probability of cure, or 33% higher risk of unfavorable outcome. And this translated in our model to a 77% relative probability of cure at a forgiveness threshold or forgiveness value of 90%. For other regimens, we then varied this forgiveness threshold, but we kept this 70% relative probability of cure. And so what this essentially looks like is a kind of very simple step function where if you're above the forgiveness threshold, you got the full probability of cure, still adjusted for early discontinuation. If you're below the threshold, you get hit with this 77% relative probability of cure. Again, very simple relationship for lack of better data, but I think there is more of this type of data coming out now in the literature, so hopefully we'll be able to update this in a future approach. So this table just shows what we assumed about these 4 regimen characteristics for the standards of care, and then trying to match TRP targets for the minimal and optimal characteristics. Efficacy data came from clinical trials for standards of care. Ease of adherence data, percentage of patients by adherence category, came from a digital adherence monitoring study for HRZE and forgiveness. I just talked about came from that TB Reflect study. And then we don't have as much evidence for BPAL-BPAL-M. So based on its side effect profile, we assumed slightly less optimal adherence. And based on the PK properties of drugs in the regimen, we assumed slightly better forgiveness. And then the minimal and optimal values here were trying to align with the TRP targets to the extent possible, or preliminary TRP targets. Our main analysis of health outcomes here was focused on patient cures, but as part of cost analyses and to estimate secondary outcomes like mortality in secondary cases, we added a post-TB or post-treatment component to the main model. So everybody exits the main model either durably cured or not durably cured. For those who are durably cured, we don't really follow them up further, but we do assume they accrue some post-TB mortality and morbidity. And for those who are not durably cured, a proportion of them are assumed to have died during treatment. Those who remain alive generate, on average, 1 secondary case over a simulated serial interval, and then both the primary case and the secondary case face competing risks of case detection and case fatality. And those who are detected, the retreatments are assumed to face worse outcomes and higher costs. The secondary cases are assumed to have these sort of same average outcomes as a primary case and the same resistance profile as the primary case. Our estimation of costs was essentially another add-on to the main treatment model that I already talked about. And again, the goal of this cost estimation was to estimate price thresholds at which these hypothetical novel TB regimens would be cost neutral or cost effective compared to the standards of care. We varied the time horizon in the cost neutrality analysis. So medium-term analyses considered costs of retreatment and secondary cases over 5 years, whereas short-term costs just considered costs during that patient's treatment course. And then the cost effectiveness analysis estimated prices at which the incremental cost effectiveness ratio of the novel regimen would equal a willingness to pay or cost effectiveness threshold for each country. We conducted an ingredients-based costing approach that essentially multiplied country-specific unit costs by regimen-specific quantities of treatment inputs. The unit costs came from Value TB and other published studies. And then for the standards of care, these quantities of treatment inputs, so this would be things like number of lab tests, number of outpatient visits, came from country and global treatment guidelines. And then for the novel hypothetical regimens, we assumed that a lot of these quantities of treatment inputs would scale with regimen duration. So regimens of shorter duration would require fewer outpatient visits, lab tests, et cetera, as well as some of them scaled with regimen safety. So particularly things related to adverse event detection and management. And then finally, in the medium-term analyses where we're considering costs of retreatments and treatment of secondary cases, those costs would scale with everything that determined patient cures. So they would scale with efficacy, duration, adherence, and forgiveness. Okay, so moving on to the main results of this first analysis. This slide shows the percentage of patients that were estimated to be durably cured after an initial treatment attempt under the standards of care and then under regimens meeting all of the optimal targets. We have RIF susceptible on the top here and RIF resistant on the bottom. So under the standard of care of 6-HRZE for most patients, we estimated that around 83% of patients would be durably cured. This is compared to 95% clinical efficacy of the regimen. So this gap between 95% and 83% is essentially what we attribute to early discontinuation and inadherence. And for BPAL-M, we estimated 78% of patients would achieve durable cure compared to 89% clinical efficacy. This was relatively similar across countries, which is why I'm not showing it for each country. And the main reason for this is that most of our parameters that did vary by country were parameters in either the post-treatment model or the cost analysis. In future iterations of this, I'd like to model more country varying loss to follow up, but for simplicity, we didn't really include that here. And then we estimated that fully optimized regimens meeting all of those optimal targets I showed in the table a few slides ago could increase the percentage of patients durably cured to 98% for RIF susceptible TB and 96% for RIF resistant TB. Of course, we're not at all likely to develop a regimen that meets all of the optimal targets simultaneously in the near future. And what we're really interested in here is which of these characteristics most affect our outcome of patient cures. So those results are shown here. This is essentially a series of one-way sensitivity analyses constructed in a couple of different ways. So on our x-axis here, we have the percentage of patients durably cured. We have RIF susceptible regimens on top and RIF resistant regimens on bottom. And then this sort of first panel here, the dashed line shows our estimated percentage of patients durably cured from a fully optimized regimen. Remember, that was 98% from the previous slide. And then these bars examine how that percentage of patients durably cured would vary as we vary one characteristic at a time and hold the others fixed at their optimal values. Then this bottle panel here essentially shows the opposite. So the dashed line here is our estimate of patient cures under the standard of care at 83%. And the bars then show how we estimate that percentage would increase if we optimized one regimen characteristic at a time. So what we can see here is that adherence is coming out as mattering the most. It's the most influential characteristic in 3 out of 4 of these analyses. And then the next most influential characteristic tended to be efficacy, or in some analyses, forgiveness. Forgiveness was not at all influential in the analysis where all other characteristics were optimized. And this is because our optimal value for ease of adherence was essentially perfect adherence. And so it doesn't matter what happens to patients who don't have perfect adherence in that analysis. And so forgiveness didn't matter here. I want to talk a little bit about why adherence is coming out as most important here, because it's partly a function of what we assumed about a plausible range for all of these characteristics, but it's also partly not. So we did assume in this analysis that the optimal adherence value was 100% of patients taking 100% of doses. That is pretty optimistic. It could potentially be in line with a one-time long-acting injectable, but we're not really at the point where such a regimen is being developed. So again, this would be very far in the future. But also we can see that adherence is sort of the area where we have the most room for growth in this model. So in our model for RIF susceptible TB, for instance, we estimate that around half of patients are taking less than 90% of doses while remaining on treatment. And so that's potentially half of patients whose treatment outcomes can be improved if we increase adherence. Efficacy is already high at 95%. Forgiveness improvements are only going to benefit kind of this middle tier of patients with not terrible adherence, but not perfect adherence. And then discontinuation or duration, there's only between a 6-month regimen and a 2-month regimen, only around 4% of patients that are going to, in our model, discontinue early under the 6-month regimen and not under the 2-month regimen. And so there's sort of the most room for growth, or the most potential to help a bigger proportion of patients as we adjust adherence in this model compared to some of the other regimen characteristics. Okay, moving on to the cost analysis. So first, we estimated costs under the standards of care, and we estimated that the average cost per patient treated would range from around $450 in India up to $730 in South Africa. And this includes the costs of drugs themselves, other sort of health system components of treatment, like treatment visits and laboratory tests, a lot of costs that would be non-medical costs borne by patients. So those are shown in pink and purple here and made up a really large share, especially of RIF-susceptible costs. And then in orange and yellow, we have the costs of retreating a small proportion of these patients who fail treatment and secondary cases generated by those patients. We then estimated how expensive fully optimized regimens could be such that they would produce the same total treatment costs as the standard of care. So these are our cost neutral prices in the medium term. And again, we estimate that prices of these regimens could be higher than the standard of care because we're achieving savings in other treatment components. So fewer patient-borne costs, fewer lab tests, better patient outcomes, and so less treatment of secondary cases and retreatments. These medium-term cost-neutral prices ranged from around $190 in India up to $380 in South Africa, compared to a price for HRZE of $46 at the time of this analysis, at least. I think the price is still similar to that. So around 4 times up to 8 times higher than the price of HRZE. For RIF-resistant TB, total costs were a lot higher under the standard of care. It looks like I forgot to include the labels here, but they were around $2,100 up to around $3,700. Drugs themselves made up a larger share of the total. So when we conducted this analysis, B-PAL-M cost for $430 per full course, so around 10 times higher than HRZE. Treatment outcomes are worse, and so treatment of secondary cases and retreatments also makes up a larger share of the total. And then in some countries, this varied a little bit. We start to see more costs from inpatient care and from patient support vouchers. This means that our cost-neutral prices for a fully optimized RIF-resistant regimen are also higher than they were for the RIF-susceptible regimen. So this is our sort of estimate of savings that could be achieved from fully optimizing these regimens, meaning that these regimens could be cost neutral at prices ranging from $1,200 to around $2,000. So around 3 to 5 times higher than the current price of B-PAL-M. And we also conducted this analysis, again, under varying perspectives and time horizons. Thresholds were unsurprisingly lower in a short-term perspective when we didn't consider savings from averted retreatments and secondary cases, and they were also lower under a health system perspective that didn't consider savings that would be borne by patients. Thresholds were much higher, again, relatively unsurprisingly, in the cost effectiveness analysis. And in some cases, I would say somewhat unrealistically high, right? So we're getting cost effective prices in the $6,000 to $9,000 range for South Africa. It may be the case that regimens at that price would be cost effective, but it seems unrealistic that a lot of countries would be introducing regimens if they did cost this much. And so we focused more on the cost neutral thresholds for that reason. And then we also conducted this analysis of which characteristics most influenced savings and thus most influenced the cost neutral price thresholds. Sort of same structure as the previous analysis that I showed you. And now we can see that duration is really coming out as the most important characteristic here. Again, this is pretty unsurprising since we assumed that a lot of these cost components would vary most with regimen duration. And then the next most influential characteristics were adherence and generally efficacy. And this, again, is through primarily the impact of those characteristics on patient cures and thus their impact on savings in the form of fewer retreatments and fewer secondary cases. Okay, so that was part one. Now I'm going to move on to part two, which will be quicker because a lot of it built on the same methods. And remember, in part two, we're focused not just on characteristics of individual regimens, but broader regimen strategies, including a pan-TB regimen strategy. So the motivation here is trying to answer the question of how much we should prioritize the development of a potential pan-TB regimen that could treat most forms of TB regardless of drug resistance, or could at least treat both RIF-susceptible and RIF-resistant TB relative to other potential regimen improvements. And there are a few potential benefits of a pan-TB regimen or pan-TB strategy. So the kind of obvious benefit that we think of is that right now there are patients with RIF-resistant TB who aren't receiving DST and are getting assigned to a rifamycin-containing regimen and have very poor outcomes there. If we had a non-rifamycin-containing pan-TB regimen, then we wouldn't have this problem of sort of improper regimen assignment. A pan-TB regimen could also simplify the pre-treatment care cascade by removing the drug susceptibility testing step, and this could reduce both pre-treatment loss to follow-up as well as costs. And then we looked at pan-TB regimens that met the target regimen profiles, and so these pan-TB regimens would represent improvements both over the RIF-susceptible and RIF-resistant standards of care. And so what we wanted to look at here was how much impact we could gain from a pan-TB regimen relative to each of these four potential benefits on their own. To conduct this analysis, we did some modeling that was really quite similar to part one, but with some add-ons. So we have different regimen scenarios, again, designed to unpack those four potential benefits of a pan-TB regimen. Because we're now modeling RIF-susceptible and RIF-resistant patients together, not as sort of separate cohorts, we need to keep track of underlying population-level trends in drug resistance, and we need to model what happens before patients are assigned to regimens, so drug susceptibility testing, pre-treatment loss to follow-up, and resulting regimen assignment. And then the final kind of change here is that during treatment, now we have patients who might be assigned to a regimen to which their TB has resistance. And so we need to make sure that probability of durable cure is also adjusted for that resistance. So our regimen scenarios are outlined here. We had a status quo scenario kind of similar to the standards of care in the part one analysis. We have three pan-TB regimen scenarios. The main one considers an oral regimen meeting the pan-TB TRP without any confirmatory drug susceptibility testing, so just all patients receive the pan-TB regimen. And then we modeled variations of this with confirmatory DST and with sort of optimized discontinuation and adherence. And this was added kind of based on the fact that we saw that particularly optimized adherence had such impact in the part one analysis. And then these four isolated improvement scenarios are, again, designed to evaluate how much impact from the pan-TB regimen comes from each of its four distinct benefits. So to unpack this, we modeled scenarios in which it was the same as standard of care or status quo, but we just fully optimized the RIF-susceptible TB regimen or fully optimized the RIF-resistant TB regimen, or improved the pre-treatment retention of RIF-resistant TB patients, or improved the assignment of RIF-resistant TB patients so that nobody with RIF-resistant TB would receive 6-HRZE. Based on regimens that are currently in development, we assumed that the potential pan-TB regimen and the RIF-resistant standard of care, BPAL-M, would share drugs and or drug classes, and this led us to model two main resistance categories. The first was rifampin resistance, and then the second was resistance to novel drugs. The novel drug resistance parameters were mostly based on data from bedaquiline, with the sort of assumption that if we develop a pan-TB regimen in the near future, it would likely contain bedaquiline or another dialquinoline. And in particular, we assumed that patients who have novel drug resistance but receive either the pan-TB regimen or the RIF-resistant standard of care have a 77% relative risk of cure. So that's sort of our resistance adjustment factor. Trends in the underlying prevalence of drug resistance were modeled non-mechanistically as a sort of assumed temporal trend over time among treatment-naive patients. And in the primary analysis, we modeled a maximum increase of 1 percentage point above baseline levels over 10 years, but that increase would be scaled by the proportion of patients that received a regimen with a particular drug. So, for example, if half of patients over 10 years received rifampicin, then we would model a 0.5 percentage point increase over baseline levels. And novel drug resistance was stratified by rifampicin resistance stratus. So as a result, we sort of have 4 main resistance categories in this model: pan-susceptible, RIF-resistant, novel drug susceptible, RIF-susceptible, novel drug resistant, and then resistant to both rifampicin and novel drugs. So the assumptions that we're making in our underlying trends in resistance prevalence analysis resulted in sort of what is shown on this slide here. So under the status quo, where most RIF-resistant patients receive BPAL-BPAL-M and most RIF-susceptible patients receive HRZE, we estimated almost a 1 percentage point increase in the prevalence of RIF resistance across all 3 countries, and a less than 1 percentage point increase in the prevalence of novel drug resistance among RIF-resistant TB patients. And again, this is because some RIF-resistant TB patients would not receive BPAL-BPAL-M because they would not have their resistance detected. We have no RIF-susceptible patients receiving novel drugs in the status quo scenario, and so that resistance prevalence was flatlined. And I should mention that this 1 percentage point increase was assumed based on global prevalence of rifampicin resistance over time. But these sort of trends were modeled in a lot more detail in another analysis that Finn led, and we're also going to be kind of considering these more explicitly in a follow-on analysis. Under the pan-TB scenario, nobody's receiving rifampicin, so we don't have any increase in rifampicin resistance over time, but we do have a 1 percentage point increase in novel drug resistance among both RIF-susceptible and RIF-resistant TB patients. In addition to the resistance prevalence trends, the other main component that we added from part 1 was a model of the pre-treatment cascade of care. That was a pretty simple decision tree model that's shown here. So under the status quo, we have RIF drug susceptibility testing steps and then pre-treatment loss to follow-up steps, where that pre-treatment loss to follow-up is higher for those who receive the RIF DST and get assigned to a second-line regimen. And on the right, this kind of shows what that results in terms of regimen assignment for each of the patient resistance phenotypes. So patients who are pan-susceptible or have no resistance would, for the most part, get assigned to an appropriate regimen, which would be 6-HRZE. But some patients with RIF resistance would inappropriately receive HRZE, and we also have higher levels of loss to follow-up among those with RIF resistance than no RIF resistance. And then similar for novel resistant patients, we have hardly anybody with novel resistance but RIF susceptibility under the status quo, but all of them would receive appropriate regimens. And then we have no perfect regimen assignment for this group of patients with RIF and novel resistance. So they're all receiving either HRZE because they didn't get DST or BPAL-BPAL-M because they did get DST, but they are resistant to the bedaquiline component. We did model a very small percent as receiving bedaquiline DST and getting individualized regimens, but I think this was almost a negligible percent. Compared to the status quo, in the pan-TB scenario, we remove the drug susceptibility testing step and have lower loss to follow-up. And this means that more RIF-resistant patients end up initiating an appropriate regimen, but now those with novel resistance and RIF susceptibility are receiving a regimen to which they are resistant. Again, we estimated that this would only be 0.2% of all patients at baseline, but would increase over time under the PAN scenario. Okay, so moving on to results, this figure shows the percentage increase in cures after an initial treatment attempt under each of the regimen scenarios compared to the status quo or standard of care scenario. So under the standards of care, we estimated that around 70% of patients would be durably cured after an initial treatment attempt. And we can think of this as a sort of weighted average of the estimates of percentage cured from part one, with the addition of pretreatment loss to follow-up and with the addition of including RIF-resistant patients who receive HRZE and have poor outcomes. Under the pan-TB scenario, again, this is the main one with an oral regimen and no confirmatory DST, we estimated that the percentage of cured after one treatment attempt could increase to around 75 to 76%. And under the isolated improvement scenario, where we just have the status quo, but with a fully optimized RIF-susceptible regimen, we estimated almost the same increase in percentage cured as with the pan-TB regimen. The other isolated improvement scenarios that primarily affected patients with RIF-resistant TB had relatively little impact compared to the standards of care, so not much increase in cures. And then adding confirmatory DST to the pan-TB scenario didn't really change the results of the pan-TB scenario, similar increase in percentage of patients cured, but optimizing adherence and eliminating discontinuation, such as could be achieved via a one-time long-acting injectable, consistent with the part one analysis, had a big impact and further increased the percentage cured above the main pan-TB scenario. We also looked at outcomes of mortality in secondary cases, and I'm not going to spend much time on these, but just want to say that these tracked very closely with our estimates of cures in terms of the relative magnitudes of impact. And then we also estimated costs. So average cost per patient under the status quo were estimated to range from $470 per patient in India up to $800 in South Africa. I've only shown India here just to make the graph a little bit easier to see. And again, we can think of this as kind of a weighted average of the standard of care costs estimated in the part one analysis. A pan-TB regimen was estimated to reduce non-drug costs. So here we'd be comparing this part of the bar before the black, which is drug costs, to this bar here by between 32 and 42%. And savings were pretty similar in the other pan-TB scenarios and less in the isolated improvement scenarios, particularly those that improved outcomes for RIF-resistant patients. And we also estimated cost neutral thresholds in this analysis, and these ranged from $170 to $340 for the sort of main pan-TB regimen. So that regimen, to put this in context, would have to cost less than BPAL-M to be cost neutral. And these results looked, again, relatively similar across countries. Total costs were higher in, say, South Africa than India, but the sort of extent to which these different regimens produced savings of different magnitudes was similar across the countries. So as in part one, I just wanted to provide a little bit of intuition for why we're getting these results, and specifically why we get such a large impact from an improved RIF-susceptible regimen and barely any impact from the other isolated improvements that we considered. And the main reason here is just that most TB, globally and in the three settings that we modeled, is RIF-susceptible TB. And so in an analysis that considers the entire population of TB patients together, a given level of improvement for RIF-susceptible patients will be more impactful than the same level or an even greater level of improvement for RIF-resistant patients. And this set of graphs here shows that outcomes are improved more for RIF-resistant patients from the pan-TB regimen than RIF-susceptible. So this is sort of the improvement from status quo to pan for those who are RIF-susceptible, and this is the improvement for RIF-resistant TB. But there just aren't enough RIF-resistant patients in the analysis for this to outweigh the impacts for RIF-susceptible TB. Another interesting observation here, focusing on the bottom set of graphs, is that the pan-TB regimen is estimated to improve RIF-resistant TB outcomes much more than any of these isolated improvement scenarios. And this sort of indicates to us that improving the existing regimen, improving regimen assignment, and improving the pre-initiation cascade of care are sort of all priorities for RIF-resistant TB, and we need to improve all of them to have a lot of impact here. In future analysis, we're going to more formally consider equity across patient groups so that we can make sure we're kind of valuing these bigger improvements for this smaller subgroup of patients. So to summarize, in the first analysis, we wanted to analyze which regimen characteristics were most important or influential, and we found that ease of adherence and efficacy were the most influential determinants of cures, while duration, followed by ease of adherence, were the most influential determinants of savings. And then in part 2, we wanted to estimate which components of a pan-TB regimen or pan-TB strategy were most impactful. And we found that most of the population level impact and savings, to a lesser extent savings, to a greater extent impact of a pan-TB regimen could be achieved via a really optimized RIF-susceptible regimen. And as in part 1, the analysis of the long-acting injectable showed that optimized adherence does extend regimen impact. A lot of limitations to this analysis, a lot of simplifying assumptions that we made. I'm just going to quickly touch on a few of them. So these results are likely not to generalize to children, extrapulmonary TB, or other special populations. We were really considering adults with pulmonary TB here. Which characteristics we would prioritize really depends on the extent of improvements, and we tried to ground these in the target regimen profiles. But again, when future regimens become available, we really don't know what their improvements will be in terms of efficacy, duration, ease of adherence, et cetera. We have really limited evidence on forgiveness and adherence under the standards of care, particularly for BPAL, BPAL-M. And these results, particularly the second set of results, are unlikely to generalize to settings with a very high prevalence of XDR-TB, where a pan-TB regimen strategy, at least one that contains drugs like bedaquiline, is likely to be less feasible. Cost neutrality doesn't necessarily translate to affordability for health systems. Even under the health system's perspective, we don't expect that all of the savings that we project from an improved regimen would accrue immediately or to the same payers. So we see some of them, for example, accruing to patients. And the thresholds that we estimated are likely to decline as the standard, or will decline as the standard of care drug prices decline. And I think we've already seen declines in the price of BPAL. And then finally, several important considerations were modeled here in a very simplified manner, including the evolution of drug resistance over time, the experiences of people on TB treatment, which we really only valued in this analysis through their impact on adherence, but lots of the features of regimens that would be valued by people with TB matter in and of themselves beyond just their impact on adherence and probability of cure. And then long-term population outcomes like incidence, secondary cases, and mortality were also modeled in a simplified manner. I know I'm a little over the time I projected here, so I'd just like to quickly close by acknowledging collaborators and co-authors here, some of whom are on this call. Thank you for joining. And then also funding from the Bill and Melinda Gates Foundation and the World Health Organization. Thank you.
Fantastic. Thank you so much, Tess. That was really interesting and a lot to cover, but some really, really interesting work. We've got 7 minutes for questions. And while you all think of questions, I guess I had one that I don't know if there's really an answer to, but I was really interested in the first part that most of your benefit came from the improved adherence, right? But what we've seen from lots of, and it's only sort of peripherally linked to this, but lots of the adherence technology trials. There've been a couple of big trials recently that have come out. The one in China, and then there's the Ascent one as well. And broadly, before we've had trials that show that adherence technologies improve adherence, but these trials have measured outcomes. And I think you were potentially looking at sort of step wedge trial in Uganda or something. I assume is the one you based yours on. But a lot of the big trials have shown that although adherence is improved, it doesn't actually improve outcomes. And so obviously that's a part of what you have there with the TB Reflect. I can't remember the one that the link between adherence and outcomes. And I don't have an answer to this, but it kind of makes me wonder, like, you know, if we had things which could improve adherence like this, is it going to make any, would the treatment regimens, is that going to make any difference to the outcomes, or is the issue actually elsewhere?
Yeah, it's a really good question. I don't think I have a great answer to it either, but I think a couple, I guess, pieces of food for thought. I mean, one is that it probably really depends on the extent of the adherence improvements and where, like, how adherent somebody would be absent the technology and how adherent they would be with the technology. And if in our analysis, if that kind of pushes them over this threshold, it would help them. But in reality, if we're only seeing a little bit of an improvement in adherence, we would expect to see that adherence outcome improve, but we wouldn't necessarily expect that to translate into better treatment outcomes. I think another point is the extent to which we can trust some of the data coming out of adherence technologies. And that's obviously going to be a limitation in our analysis too, because we're assuming that those adherence categories in TB Reflect, for instance, are an accurate representation of the percentage of doses that patients are taking. And then another is this question of like when the doses are missed. So we're sort of assuming that this is like intermittently missing doses, and maybe you're taking 6 out of 7 of your doses every week. But if instead you're sort of missing doses for like 3 weeks and then perfectly adherent after that 3 week period, that's going to look the same in terms of percentage of overall doses taken, but probably is going to have a big impact on treatment outcomes. So yeah, not really an answer, but I think there's lots of complexity here that could be unpacked through more precise modeling of that adherence cure relationship.
Yeah, absolutely. And I mean, some of it's, you know, even improved modeling, where we need the data to help us understand it before we can
Yeah.
do much. But yeah, no, I just think that's an interesting thing just because of the results we've had in the last few years that kind of turn that on its head a bit. Nick, so you had your hand up and it's just come down.
Well, I had a long question, but I'll save that one for later. The short question is, I noticed that as you know, length of regimen mattered a lot less than I would have thought, and it made me wonder. Like essentially, you know, the people developing regimens have a different value function that you use in your model, and so if you were to, you know, in your model finish regimens a month earlier or a month later. It'd be interesting to see how that actually affected your results. Like, or if you could break people into phenotypes, like for the highly adherent patients, can you say, if we can find good, you know, if we can find a way of confirming that you've been highly adherent, maybe you get a 4 month regimen or something like that.
Yeah. Yeah, I mean that's really interesting. I'm also always kind of surprised when I see these results that duration doesn't matter more, but I mean we do just see like loss to follow-up tends to be under 10% in those in this model that we assume those are the only patients that could be helped by shorter duration regimens and only a subset of them would be. I mean, in reality, if there is correlation, for instance, between when people become lost to follow-up or their likelihood become lost to follow-up and how adherent they were before lost to follow-up, I think those correlations likely do exist and they could result in a different prioritization of duration, but we didn't look at that here. I don't know. I think with a lot of the sort of new like personalized medicine approaches and trials trying to kind of personalize things like duration more, we could be seeing more data that could inform some of this analysis that you kind of suggested, like looking at patient phenotypes. So I think that would be yeah interesting to look at going forward.
Thank you. We've got 2 minutes. Does anyone have a quick question? Or Nick, do you want to try and start your long question? I don't know how long is long.
Okay. Well, actually, I'll make an observation. Is that relevant to the last? Is I remember going back to the early isoniazid trials and look, because there's actually quite detailed reporting of them. I think what they are reporting should be questioned in terms of what it means to see those that are still smear positive and smear negative, but still, where from a lot of those trials, I was surprised. It seemed like a lot of the action was in the first kind of 1 to 3 months. They're either going to be cured or they're going to develop resistance. But one of those things, two things happened. It was about 50-50. But actually, the even for monotherapy, if they were going to be cured, it could actually happen quite quickly, which I think is consistent with, your finding that, if you get, well, I'm summarizing it for myself as if you're adherent through to the, two-thirds of the way through the regimen, you've got 80-90% of the benefit. The longer question is about the trial reported outcomes and the constructs, the sort of true health status in the model. Because, what trials report are based on the measures we have that, say, patients report about adherence, which, as you pointed to, is, should be questioned, but also in terms of the tests we conduct of patients. So just how one interprets those reported data compared to the things you want to model, given that it's sometimes not a natural link, one-to-one link.
Yeah. 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 I mean, it's a really good point, and we should maybe examine some of that data in more detail. I mean, for example, a lot of those trials didn't have very long-term follow-up, and we don't know if a lot of patients like relapsed right after the period of follow-up, and that could have varied by duration. So yeah, yeah, absolutely. It's data that we're relying on, but it does have a lot of limitations. I agree.
All right, thank you. And I think with that, it is on the hour, so we probably better wrap up so we can go on to the next sessions. But I also, just to say that this is all will be recorded and I'll stick it up online, hopefully later this afternoon on the TV Mac website. And next month we will hear from Stella, who's actually on the call with us now as well. So we'll look forward to that towards the end of February. Cool. Thank you very much, everyone, for joining. And yeah, look forward to seeing you next month.
Thanks, everyone.
Cheers. And Samia, did you just join? Oh no, never mind. Cheers.